at an elevated temperature for a longer period, for a shorter period, depending upon the reactivities of the metal and the ligand and the stability of the complex which is formed, and the kinetic requirements, the energy barrier for the reaction. Different situations require different reaction conditions, and then complexation takes place. This process of complexation has been viewed uh, generally as in a systematic manner like this, that when you add a metal salt, say cobalt chloride, you have dissolved it in water. What happens to the cobalt chloride when you dissolve it in water? You must have noticed that all salts, whether they are salts of the transition metals, or salts of the alkali metals, or salts of the main group elements, main group metals, p block metals, they exist as there is anhydrous salts or hydrated salts. So you will have calcium chloride, hexahydrate, like that, tetrahydrate, dihydrate, like this. सर पूछ रहे हैं ये चेयर में भी चार्ज ना यार चेयर पहले ये जन से डाउन करो, मेरी लाइट ही नहीं, मैं क्लास ले रहा हूँ, चेयर का बाद में सोच रहे हैं, जा जल्दी बोल, बोलो मेरी कंप्यूटर बंद हो रहा है, दौड़ के जा. So, my computer will be off anytime now. So, the salts, what happens that you dissolve, oh yeah, sure, thank you. When you dissolve a metal salt into water, the immediate effect is that the lattice energy is broken, or lattice energy is overcome by the hydration energy, and the bond between metal and the cation and anion is broken, and the cation and anion are separated, and both cation and anion get hydrated, and energies, or I would say, if the water is not solvent, I would say the term solvated, and energy is released during this process that is known as hydration energy if the solvent is water, or generally solvation energy if the solvent is any other liquid other than water. So the solubility is a critical balance between lattice energy and the hydration energy. If hydration energy is large, lattice energy is less, then obviously salt will be soluble in water. If reverse thing happens, that lattice energy is quite large and hydration energy is not high, then obviously salt is insoluble in water. So suppose the salt is water soluble in water, metal gets hydrated. What do you mean by hydrated? That metal forms a complex. We write cobalt chloride in water. We write cobalt 2 plus, within bracket we write aqueous, AQ. Cobalt aqueous means that cobalt cation, cobalt 2 plus, is hydrated. What do you mean by cobalt hydrated or cobalt aqueous? That is, cobalt forms cobalt 6 times water, 2 plus. It forms a complex with the water molecules. And that complex is known as cobalt 2 aqueous or cobalt hydrated. And then when you add a solution of the ligand to such a solution, the ligands try to dislodge, to replace those water molecules, and enjoy having a contact with the metal through a coordinate bond. Water molecules were also having the contact with the metal ion as in form of a coordination bond, and ligands are also having same sort of relationship with the metal. However, the difference is that the bond between metal and ligand has to be somewhat stronger than the bond between ligand between water and the metal. Otherwise, why should ligand dislodge or displace the water molecule from that aqueous complex? So, because ligand must be forming better bonds and more stable bonds, therefore this thing happens. So this is a sort of substitution reaction. The complex formation is a sort of substitution reaction. If you start the reaction, if you view the reaction in aqueous solution, that every metal ion, when it is dissolved in water, gets hydrated and forms sort of an aqua complex, either most of the time hexa coordinate and sometimes tetra coordinate, but most of the time hexa coordinate. And then you add the ligand solution, and ligands displace those water molecules and form the complex. This process of complex formation is sort of it's in the reversible process, that you get metal plus ligand getting the MLN, or plus water can also take that MLN and form the metal aqueous plus Ln. So the extent to which the reaction goes to left or right depends upon the relative strengths of the metal ligand bond and metal water bond. So if the metal ligand bond is stronger as compared to metal water bond, so obviously the equilibrium will go to the right. If reverse thing has happened, a reverse thing is true, that bond of metal with water is better than the bond of metal with the ligand, then obviously any metal ligand bond will get hydrolyzed, and ligand will be lost, and water will come take place of the ligand. So this process can be viewed in a form of equilibrium situation. And obviously, when you have an equilibrium situation, you can represent the overall situation by a constant, which we call equilibrium constant. So the value of that equilibrium constant is also known as stability constant of the complex, or formation constant of the complex. That's what we are going to discuss. Now I'm going to the presentation. हेलो वालेकुम वालेकुम सलाम हाँ अमित यार बोल रहा अभी मैं क्लास में हूँ बोल उसको मैंने बात कर ली नरेंद्र को बोलो मैं क्लास में हूँ अभी जैसे तुम कर तो कर लो यार मुझे मत तंग करो ठीक मैं कर लूंगा जब क्लास से फ्री होऊंगा ना तो स्लाइड विजिबल है सबको
Yes, sir. Yes, sir.
Slide is visible now?
Yes, sir.
Okay, okay. So we have a metal ligand equilibrium. As I said, that when we view the situation in terms in terms of the process, that we have the water molecules surrounding the metal ion in a particular orientation, and then we add the ligand. There is interaction between the ligand and that aqua complex, and there is a sort of displacement reaction happening, water being replaced by the ligand, and we form in complex M. Ideally, I should write here M aqueous, M n plus aqueous, or M aqueous, M water n times, and then M plus, like that, plus NL, and use this is the simple form in which we write the equilibrium between metal and the ligand. Ideally, I should have written here M aqueous. Beta is known as whenever you have an equilibrium, obviously there will be a constant known as equilibrium constant, which gives the molar concentration of the product, ratio of the molar concentration of the products and molar concentration of reactants. In a more sophisticated manner, this reaction would be M H2O n times plus NL, and here MLN plus water molecules will be replaced, and then in the numerator water molecules will appear. But then because the water will be in high concentration, excess of water is there, So its concentration does not change with the complexation process. Therefore, that is taken as constant, and we neglect that water concentration in the numerator, and we simply write the concentration of the species which have small values and which change with time, and therefore have the impact on the equilibrium constant, and therefore water is not taken into consideration. So this equilibrium constant, if it has large value, if it will have large value if the numerator has large value. Concentration of the MLN is high and concentration of metal and ligand is less. In other words, if the equilibrium goes to the right to large extent, then the equilibrium constant has large value. So we can also say that this equilibrium constant is directly proportional to the extent of formation of the complex. To what extent the complex is formed, that value will be dictated by the numeric value of the equilibrium constant. Larger the equilibrium constant, larger will be the extent of the formation of the coordination complex. So this constant can be also called, in the other sense, formation constant of a complex, because its numeric value, it gives a direct measure of the extent to which the complex has been formed between metal and the ligand. Or it all, in other words, because the reaction, there's an equilibrium, if this complex breaks down into individual metal and the individual ligand, then that gives you the instability constant, or reverse process is the breakdown of the complex, dissociation of the complex, and forward process gives the stability of the complex. So the numeric value of this equilibrium constant is also, parallel with the stability of the complex. So higher the value of beta n, higher is the stability of the complex. Lower is the value of beta n, lower is the stability of constant. So equilibrium constant for a complex gives you the measure of the extent of formation of a complex. So you can call it a formation constant of a complex, but also it can be also called stability constant of a complex. So obviously, all these things depend upon the strength of the interactions, strength of the bond between metal and ligand. If metal ligand bond is much stronger than the metal water bond, obviously the reaction will go to the right side to a large extent. And if it is reverse thing is true, then obviously the metal complex will not survive, and the beta will have the smaller value, numeric value. So complex formation cannot take place directly. If you look at the minute details, the complex formation has to take place step by step. There are 6 water molecules initially, then one ligand will come and dislodge one of the water molecule, and that process will have its own equilibrium constant. Then the second process, the 5 positions are there available. Ligand will come and it has now the 5 positions available in the equilibrium constant. Then the third process, the 5 positions are available. Ligand will come and it has now the 5 positions in the equilibrium constant. Then the fourth process, the 5 positions are available. Ligand will come and it has now the 5 positions in the equilibrium constant. Then the fifth process, the 5 positions are available. Ligand will come and it has now the 5 positions in the equilibrium constant. Then the sixth process, the 5 positions are available. Ligand will come and it has now the 5 positions
सर आपकी आवाज नहीं आ रही है.
M plus L. Second one has ML plus L. Third one has ML2 plus L. So each step has its own equilibrium constant, and the last step will be written as
Excuse me, sir.
yes,
स्क्रीन
please.
नहीं दिख रही
Sir, screen is not visible.
Okay, how come? अभी है?
No, sir.
नो सर
No, sir.
सर सर नहीं आ रही आवाज
आवाज नहीं आ रही, स्क्रीन नहीं आ रही।
तो पहले आवाज नहीं आ रही पहले आवाज नहीं आ रही थी
मैंने बंद किया अभी। पहले क्या नहीं आ रहा था?
सर आवाज भी नहीं आ रही थी पहले।
सर आप भी नहीं दिख रहे थे, आवाज भी नहीं आ रही थी।
अभी स्क्रीन शेयर हो गया?
यस सर।
यस सर
नहीं नहीं, जस्ट वेट, अभी मैंने सिर्फ स्क्रीन शेयर किया, स्लाइड नहीं। Now see, slide is visible or not?
यस
यस
सर
सर।
Yes, sir.
Okay. तो ये वाली स्लाइड हमने डिस्कस की, यू हर्ड एवरीथिंग व्हाट आई सेड?
यस
यस
सर
सर।
तो आई विल गो टू सेकंड स्लाइड जिसमें प्रॉब्लम था, है ना? मैं
यस सर
स्क्रीन
Yes,
कर,
sir.
मैंने फुल स्क्रीन किया, इट्स ओके। ओके, ये वाला स्क्रीन, ये वाला स्लाइड नहीं दिखा था आपको?
यस
नो
सर।
सर
सुनाई भी नहीं दिया था और दिखा भी नहीं था।
नाउ इट्स विजिबल ना?
Yes, sir.
Okay, you can see it now. So what I was saying that when you think of a complex formation, it does not take place as an explosion. It takes place step by step in a sequential manner. That you have a metal ion surrounded by water molecules. In particular, water molecules also are oriented in particular directions. Say there are 6 water molecules, and hexa-aqua complex has been formed when metal salt was dissolved in water, and then ligand has been added to this ligand solution of the ligand has been added to this solution. Then ligands gradually, in a sequential manner, replace water molecules and form the complexes. So this process takes place step by step. In the first, step, water molecule, one of the ligand displaces one of the water molecules. Out of the 6 water molecules, one position is occupied. So that situation, that step, has the ligand has huge choices. It can occupy, it can attack, or it can dislodge any of the water molecules, because all the 6 positions are, available to it, and they are identical. So any water molecule can be replaced by the ligand. So it will have its own equilibrium constant, that is M plus L giving ML. In the second step, there is one ligand already there. The ligand has the incoming ligand now has to replace any of the water molecules, remaining water molecules. Say there were six water molecules initially, now there are only 5. So there are 5 positions. Out of the 5 positions, it can replace any one water molecule and form Ml2. This process, this step has its own equilibrium constant, that is K2, Ml2, Ml into L. Similarly, third step, fourth step, and last step will be Ml minus N, L, Kn, Mln, and Kn, like this. So every step has its own equilibrium constant, right? The magnitude of the equilibrium constant will not be same in different steps for different reasons. One of the reasons is this, that the chances of the reaction in the first step are much larger than the chances in the second, and then chances in the second are better than in the third. And as we progressively increase the number of ligands in the metal on the metal, the chances of the reaction diminish, and therefore the uh, the the chances of the encounter decrease, and therefore equilibrium constant has somewhat lesser value. This is what logically happens, but it is not always this. We'll see the exceptions, that sometimes the successive the step has higher, the numeric value of the equilibrium constant is higher in the fourth step than in the third step. The reverse thing, that is the reverse. thing that is happening, and it has its own reasons. We'll discuss that just now. So why should this equilibrium constants having different values in different steps? One reason, as I said, that as the metal gets engaged with the ligands, the choices of the ligand, the positions of the water molecules at which the ligand has to attain, they decrease, and therefore there are lesser chances, lesser permutation combinations, and therefore less encounters, successful encounters, and therefore the equilibrium has lesser diminished value. Then that's a sort of kinetic problem rather than the thermodynamic problem, that the chances of the encounter decrease, and therefore the equilibrium constant decreases. Not that the product is less stable. Then the second problem is that once the ligand gets attached to the metal, many times the ligand has negative charge. Not always, but most of the time, ligand is negatively charged. Or even if it is not negatively charged, it's a polar molecule. It has its negative dipole. It has negative dipole directed towards the metal. So primarily we think of this situation that why should ligand approach the metal in an aqueous solution or in the solution state, that metal is a positive charge and ligand is negatively charged. If it is not negatively charged, then has a negative dipole directly towards metal, and there is sort of some electrostatic interaction between the metal and the ligand. As the ligand gets engaged with the metal, the charge density, the charge on the metal gets diminished. Say metal was +3, one ligand got attached, say it is chloride. So in the next step, metal will have the complex Ml will be the one of the reactants, and it will have +2 charges now. It will not have +3 charges as was there in the first step. So the positive charge will decrease. Similarly, in the next step, because metal is +3 and ligand is, say it is chloride, so this species will have the charge -1, a +1, and next one will be neutral. Ml3 will have no charge. So because there is no charge on the complex, or the positive charge getting diminished at every step, therefore the chances of the reaction or less. Therefore, the equilibrium does not go to the right instance. It shifts. It has lesser numeric value. So that's the reason that why the equilibrium constants have different, individual steps have different equilibrium constants. But let us concentrate on this step. So this is the third step. What does this equilibrium constant of this third step tell you? Does it tell you to what extent ML3 is formed? No, because if I talk in terms of the absolute terms, that what is the chances of the formation of ML3? ML3 formation includes first step and second step also. To what extent the first step happens, and because second step is dependent on the first step, and third step is dependent on the second step, because the reactant in the second step is what was product in the second step. Reactant in the third step is what is the product in the second step. Similarly, the reactant in the second step is what is product in the first step. So if I ask you what are the chances of the formation of the ML3, the K3 does not tell you that story. K3 is only telling you what are the chances of formation of ML3 from ML2. It does not tell you what are the overall chances of formation of ML3 from metal and ligand, because it tells you the value of the extent of the reaction of the third step only. It does not include any information of the previous steps. So this thing has to be distinguished, that the stepwise equilibrium constants have their own limitations, that they talk of in that step only. They do not include any information about the previous steps, right? So if you are asked what is the chance of the ML3 formation, you must have the knowledge of K1 and K2 and K3, then we can say to what extent the ML3 is formed. Now, K1, K2, K3, Kn, they are equilibrium constants for different steps, and they are also known as stepwise equilibrium constants or stepwise stability constants or formation constant. I mean, this formation constants of the ML3, but not from the metal and ligand, but from ML2 and L. If you are asked what is the formation constant of the ML3, that's not the K3. That is summation of K3, K1, and K3 taken together. That gives us the formation of ML3 from M and L. So magnitude of these constants tells us the extent of formation of the different species in a particular step. No information about the previous steps. The extent of formation of a complex up to a particular step, for example, ML3, beta 3 should be used. So what is beta 3? Beta 3 is M plus L, M plus 3L, giving you ML3. Just as we were using M plus Ln, beta N, beta 3 will be M plus 3L, giving us ML3. Then that beta 3 will tell you what are the chances of formation of the ML3 from metal and ligand. That will include the information of step number 1, step number 2, and step number 3. So beta 3 should be used, and beta 3 is equal to K1 into K2 and K3. So this is how beta 3 is written. K1 is ML plus this, M into L. This is K2, ML2, then ML and L. Then K3 is ML3, ML2, and this. And if you cross them, this and this will go, this and this will go. You are left with ML3 only in the numerator. In the denominator, you have metal 1 times here and ligand 1, 2, and 3. So it is ML3 and it is beta 3. So beta N. So we generalize the situation. Beta N overall equilibrium constant of any complex or any n steps is equal to K1 into K2 into K3 up to the Kn. So if you take log of the equilibrium constants, generally equilibrium constants are very small, have some small values, and therefore we take the log, and log beta n will be log of mn is equal to log m plus n. So K1, K2, K3, and this. So log beta n is equal to n varying from 1 to n log summation of the log Kn. So this is the relationship between stepwise equilibrium constants and overall equilibrium constants. So example is copper tetraamine, copper plus 1 amine. This is first step equilibrium constant here. Then second step equilibrium constant here. Then third step equilibrium constant here, and fourth step. And in one step overall equilibrium constant is written as 4NH3, this and this. So for the first step equilibrium experimental values for first equilibrium constant is 4, second is 3.2, third point. You can see that there is progressive decrease in the values of the equilibrium constant as we move from K1 to K2, K3, and K4. And the beta 4 is summation of these, and this is 11.9. And generally, if the equilibrium constant has overall equilibrium constant has value more than 8, it's called a stable complex. If it is less than then, that is not called a stable complex. So 11.9, thermodynamic stability is directly proportional to the overall equilibrium constant. Beta n greater than 8, thermodynamically stable. Copper has high stability, copper tetramine. So dissociation and instability constants are inverse proportional, reciprocal of the overall equilibrium constant is given called dissociation constant. So you take the reciprocal, you are generating the instability constant or dissociation constant. So what are the trends in this stepwise equilibrium constant? General trend is that there is successive when you go from K1 to Kn, the order is like this. This is general trend that is expected. K1 greater than K2, K3, K4 like this. So the reason is decrease in number of coordination water molecules as ligands to be replaced by the taking ligand. That's one reason. then decreasing ability of metal ions to attract the ligands due to progressive intake of ligands, the Coulombic interactions, diminish, and steric hindrance also diminishes the interaction between metal and ligand. Many times ligands are large enough, they generate an steric hindrance of hovering around the metal ion and don't allow the incoming ligand, the additional ligands to take the metal water molecules. So that's also the reason why the equilibrium constants have this diminishing effect as we go from one step to second step to third step. So the copper in this example again, this is first step, second step, nothing new. So K3, K4, and these values, there are hexamine, hexa aqua has 6 sites for available. Actually, copper forms this complex when you have treat with the copper sulfate, you dissolve in water, it forms hexa aqua complex. And when you treat with ammonia solution, you generate this. This is the ultimate complex. Four water molecules get displaced by the ammonia, and 2 water molecules are far distant at a quite distance. The complex is practically 4 coordinated, but then if you take the long distances into consideration, then it is also 2 water molecules are also there to complete the hexa coordinate. So ideally, we say normally it's a square planar complex. So that's the reason. And then exceptions. Many times reverse thing also happens, that the K4 in a complex which has 4 stepwise equilibrium constants, K4 has higher value than the K3. That also happens. And what are the reasons for such behavior is that there are many times unusual structural deviations. For example, in the previous complex, when you have the 4th equilibrium constant, you have 3 water molecules and three ammonia molecules. Up to that, this is the complex starting material plus ammonia. The next complex that is formed is ammonia plus these 3 water molecules are lost. Not only one, but these are also literally lost. So there is huge structural change at that point in time. Initially the solution, the copper complex was hexa aqua. It's an octahedron complex, and ultimately you form an tetraamine complex, tetraamine copper 2 square planar complex. So when there is huge change in structure, then that step becomes quite that has equilibrium constant quite large. So variation in electronic structure of the metal. Many times there is huge change in the electronic structure. For example, change in crystal field stabilization energy. I hope you know the concept of crystal field stabilization energy. Do you know? Shanu Sharma? Shanu? Shanu?
Yes,
शनु
sir.
अपना आप बोल सकते हैं, अपना वीडियो ऑन करो. व्हाट इज क्रिस्टल फील्ड स्टेबलाइजेशन एनर्जी? अपना वीडियो ऑन करो.
Sir.
शनु?
Yes, sir.
हाँ. Can you tell us what is crystal field stabilization energy? Shabash.
Sir,
No?
sorry, sir. इस मुझे नहीं आता है.
Okay. Who's the next roll number 2?
Yes, sir.
हाँ.
Sir, I think it is related to the differences between T2G and EG energy levels.
Okay.
T2G and EG energy levels.
Putra, that is crystal field splitting energy. I
Ji,
am
sir.
talking of crystal field stabilization energy.
Ji, sir.
Have you heard this term?
Sorry, sir.
No? Okay. Who's next? Roll number 3? 3. शनु शर्मा प्रसन्नजीत के बाद कौन है? अनी जमवाल, प्रियंका चौधरी. आप हो यहाँ? प्रियंका चौधरी is here. अनी जमवाल, मनीषा, इरम सबा है?
sir.
इरम सबा. Yes.
Yes.
अपना वीडियो ऑन करो. You tell us.
सर क्रिस्टल फील्ड थ्योरी की स्टेबलाइजेशन वाला
तो अभी तक आपने सुना नहीं मैं क्या बोल रहा हूँ?
क्रिस्टल फील्ड स्टेबलाइजेशन एनर्जी
Yes, yes. CFSE, crystal field stabilization energy. Do you know anything about this?
सर सुना है लेकिन याद नहीं है
Okay. आपने पढ़ा है?
यस सर
कहाँ? कौन सी क्लास में?
सर 12th क्लास में पढ़ा था
Oh my God. तो ग्रेजुएशन में कहीं नहीं पढ़ा?
ग्रेजुएशन में भी था 12th क्लास में भी पढ़ा है
But you don't remember.
नो सर
Okay. So, सकुल खरगे खरका सकुल भाई, where are you?
Yes, yes, sir.
भाई अपना वीडियो ऑन करो. हाँ.
सर ये कुछ क्रिस्टल फील्ड थ्योरी में पढ़ा था बट अब याद नहीं है.
Okay. अच्छा, voluntarily, is there somebody who knows it and can tell us, please? समीक्षा वेद, कोई भी किसी को है आइडिया? आई डोंट थिंक देयर इज एनीबॉडी, है ना? मुसरत, तुम्हें आइडिया है कुछ?
Yes, sir. थोड़ा
हाँ,
बहुत.
बताइए प्लीज.
So the crystal field stabilization energy is defined as the energy of electrons confining in the ligand field minus the energy of electrons confining in the isotropic field. Delta E minus
What do you mean by isotropic field?
isotropic field.
नहीं, अच्छा. और कोई भाई? प्रसन्नजीत को और हो गया. कौन है? ये मुसरत, तुम्हारे दो फोटो क्यों आ रहे हैं यार?
एक्चुअली में मैंने पीसी से ज्वाइन किया है सर, इसलिए.
ओके, ठीक है. तो ऐसा है कि अपना व्हाट इज क्रिस्टल फील्ड स्टेबलाइजेशन एनर्जी? नॉर्मली वी से the stability which a molecule achieves during the bond formation is related to the strength of the bonds. Is that okay? If the bonds are very strong, then the molecule is potential energy drops. जैसे the story started with the two hydrogen atoms, जो भी bonding theories develop हुई, valence bond theory वगैरह. When two atoms were, you must have seen that energy diagram. On the y-axis we plot potential energy. On the x-axis we plot the interatomic distance. When two atoms, hydrogen atoms, are far away, the potential energy is quite high. As you bring them together, there is interaction between them. The bond formation takes place. The potential energy dips, and when you push them more towards each other, then potential energy again increases. So there is a minimum in the potential energy at a particular distance, and that distance is called bond distance between two hydrogen atoms, right? So the stability of a molecule is related to the bond energy. If the bonds formed are very strong. A nitrogen molecule N2 is called an inert gas. It's not reactive. It is reluctant to react because bonds are quite stable. Bond between two nitrogen atoms is quite stable. It's a strong bond, and therefore any molecule which has strong bonds will not react easily. So weak bonds are more reactive. So the stability of a molecule is related to the bond energy. How much energy? What is bond energy? The amount of energy which is released when the bond was formed. Same amount of energy is required to be invested when the the bond has to be broken into fragments, right? So that is the general story about the bond energy and the stability of the molecules. But in the case of coordination complexes, it was found that the stability of the complex uh, depends upon the strength of bonds. That is true here also, but there is extra stability achieved by the coordination complex by simply rearranging the electrons which are not those electrons which have not participated in the bond formation, which are sort of non-bonding electrons, into the separated d orbitals. That rearrangement of the electrons in the separated energy levels, which is the consequence of the complex formation, that's the extra stability achieved by the complex by rearranging, the redistributing the electrons which are non-bonding, which have not participated in the bond formation. This special stability and stabilization energy is known as crystal field stabilization energy. It is called crystal field stabilization energy because the origin lies in the crystal field, that these d orbitals were splitted. If there would have been no splitting, there would have been no crystal field stabilization energy. This stability is governed by, is the root cause of this stability, extra stability, is the splitting of the d orbitals. And then we rearrange those, redistribute electrons which are not which have not participated in the bond form. That is the special thing, that normally the stability is given to a molecule by the bonding electrons. To what extent the molecular orbital, bonding molecular orbital, has lower energy than the combining atomic orbitals. जितना molecular orbital जो bonding molecular orbital है combining atomic orbital से नीचे होगा energy में, उतना molecule की stability ज़्यादा होगी. If the bonding molecular orbital is not that much stable, then the combining atomic orbital, we see the bond is not so stable. But here, the stability is given by the electrons which are not participated, which have not participated in the bond formation. That's why we call it crystal field stabilization energy. So many times, the exceptional this reversal happens in the case of uh, the the stepwise equilibrium constants because of the crystal field stabilization energy. We'll continue it next time. So if there's any question, I can answer them.
सर ये
Hello.
कौन सी बुक से पढ़ाया?
ये किसी भी बुक में, even you can consult Indian author books also, because this is primarily, this is not so conceptual, चीज. ये तो अपना किसी भी बुक में, I don't think इसमें होगा, हुई में भी होगा, but not to that extent. We will write anything in a very concise manner, in an abstract manner, but you can consult any Indian books also which are available if you want to write, study in detail. There is one book, Greenwood, also. It's also there, but I don't think it is in the J.D. Lee. In that book, you may not find this topic there. Okay.
ओके सर.
Okay, I'm logging out. Okay. Bye.
Okay, sir.
Thank you, sir.